Welcome back, students. In this video segment, we will take a look at section 5.1, linear transformations. Before we get started, though, I want to put this chapter in kind of perspective into where it kind of fits into the course. Well, it's easy to do that. We're returning to vector spaces. We're going to be returning to the study of that involves vector spaces. So, in terms of the level of difficulty of this material, it's up there in terms of difficulty with vector spaces, because we are going to be studying aspects of vector spaces again. So I hope you enjoyed our little excursion away from vector spaces into differential equations. We'll be coming back to differential equations in chapter 6 and 7, but plan on spending quite a bit of really quality time on chapter 5. Okay. So without further ado, let's get started. What is a linear transformation? A linear transformation. Before we talk about a linear transformation, let's talk about just a transformation, not a linear transformation, just transformations. Transformations are functions between vector spaces. And if that doesn't make sense, no worries. I'm gonna give you an example. We've studied you've studied a couple of kinds of transformations before this course. If you had Calc 3, you've studied at least 2 or 3 kinds of transformations. If you haven't had Calc 3 yet, then you've studied a kind of transformation. You've studied, and don't panic about this notation. You've studied transformations, functions between 2 vector spaces. You've studied functions which take an element of R, a real number, and turn it into another real number. This fancy notation just says that the function maps R into R, or the function takes a real number and turns it into another real number. And it's a standard notation for transformations between vector spaces and stuff. So, but it's not anything really complicated. So, for example, let's let f of x equal x squared. This function takes a real number, x, and turns it into another real number, x squared. Let's see. I was going to think of another one, but I think we'll dig right into where we're headed. We're looking for the idea of a function that doesn't just take a real number into another real number, but a kind of function that takes an element from one vector space. We would like to have a function that takes an element from one vector space, takes an element from one vector space and turns it into an element in another vector space. So where V and W are vector spaces. Vector spaces. Okay, so I thought it would be a good idea to look at some real simple examples before digging into linear transformations. So an example of a transformation, well, we've already looked at one, but let's take a look at a more elaborate one, something we haven't seen earlier in calculus or in pre-calculus or in math before this course. Okay, so let's say let t take y and turn it into y prime. So t takes a function, a certain function, and turns it into another function, turns it into the derivative of the function. Well, the domain of this transformation obviously can't be any function, because not every function has a derivative. So this transformation is taking a very specific vector space into another very specific vector space. Let's take a look at what those 2 vector spaces are. So let's in this square or in this rectangle, let's put the elements of the first vector space of the domain of this transformation. We're not going to call them functions anymore. We're going to call them transformations because that's the notation that's the verbiage that we use, the terminology that we use in linear algebra. So this represents the domain, and this represents where the domain is taken. The elements from the domain are taken. So let's say this dot here is an element from the domain. It would be a function. And you take that function and you apply t to it, and it turns it into something in the range of the transformation. It turns it into y prime, okay, which I could represent as another dot if I wanted to. So here's another element of this first vector space, a specific one, x squared. T takes x squared and turns it into 2x. T takes, I could totally do without the dots, I guess. T takes cosine x and turns it into negative sine x. So notice what t is not doing is you don't enter specific numbers for these functions. This transformation takes not numbers into other numbers. It takes entire functions into an entire other function. So what does t take the function y equals 0 into? Now this is not the number 0. This is f of x equals 0. This is an entire function. Okay, well, what's the derivative of 0? It is 0. So the elements in the domain of this function are very specific, or of this transformation, are very specific kinds of functions. What kinds of functions are there? They are differentiable functions, and we have a notation for that vector space. The set of all differentiable functions we designate as either D or D in the superscript 1. Okay, I'll just say D. So what is the function mapping into? Where are these elements from the domain going into? What vector space are they going into? You might think, well, they're going into D again. Well, not necessarily. Each of the specific functions, x squared, cosine x, and y equals 0, those are all differentiable, and their derivatives happen to be differentiable, but the derivative doesn't necessarily have to be differentiable itself. So the domain, or the range, would be elements from just, let's say, the set of functions. Okay, the set of functions on an interval, let's say, from A to B. Okay. All right. So the way we would designate that this transformation takes something from D and turns it into something from F to a very separate vector spaces, we would say, we write, to indicate to our reader what this function, what this function is doing, we say that T takes an element of D, A, B, and we write it this way: T takes D, A, B into F, A, B. This tells us what the domain of the transformation is, and it also tells us where the elements in the domain are taken. Okay, but it doesn't give us the rule. This just says there are a lot of transformations that go from D into F. This particular one takes a derivative. Okay. Okay, let's take a look at another one. If you find this a little confusing, you'll get used to it very quickly. We're going to be spending a whole lot of time on transformations, so don't panic if this seems entirely foreign. It is foreign for you guys. So let's take T. Let's let T now be the transformation, or in less formal terms, the function. We want to stay away from that term function for right now. That takes the column vector xy and turns it into the 2 by 2 matrix x, negative y, 2y, and 0. So this linear transformation takes what vector space and turns elements in that vector space into elements of what other vector space. Think about that for a minute. Now, and at the end of this discussion with this example, I'll write it out. But what does T take here? I'll write it out. Something for you to think about. What does T take from into from? What are the vector spaces that T takes something from and turns into? Turns the element from that vector space into. Okay, so let's take a look at a rectangle that represents the domain and where those elements from the domain are taken into. Okay, so for example, T takes the matrix 1, 2 and turns it into what? It turns it into, well, the matrix takes a column vector from R2 and takes the x component and turns it into the first row, 1 in this case, and -1. And then in the second row, we doubled the y value, so it's 2 times 2, or 4. And we leave the element in the second row and second column 0. So we would say that T takes 1, 2, and turns it into 1, -1, 4, and 0. Okay, and you could either put the parentheses in or not here. Okay. But I'm trying to get you used to visualizing transformations as taking elements of one vector space and turning it into an element from another vector space. So that's why I'm using a little rectangle to do this. So what does T take the 0 vector in this first vector space into? It takes it into 0, the opposite of 0, 2 times 0, and then 0. Okay, so we would write T takes the column vector 0, 0 and turns it into 0, 0, 0, 0. Now that's special. This doesn't always happen. It doesn't always happen that linear transformations take the 0 vector from one vector space and turn it into the 0 vector from another vector space. It's happening so far in both of our examples. Take a look at the first one. The first linear transformation takes the 0 vector from the set of all differentiable functions, which is just y equals 0, and turns it into the 0 vector for the set of all functions, which is just 0. So it takes the 0 vector in one vector space and turns it into the 0 vector from the other. Again, this is not always the case. It's a special result that happens for certain types of transformations, the ones we're going to actually deal with mostly. But that's more to come with that. So did you think about what this linear transformation is taking, what this linear transformation is doing? It's taking elements from where? It's taking elements from R2, the xy plane, if you want to view elements as column vectors, and turning them into what? Elements from the set of all matrices the set of all 2 by 2 matrices with real entries. So the vector space is taking R2, elements of R2, and turning them into elements of M 2 by 2 R. Okay. Well, let's see. Do we want to look at it? I do want to look at another one. This is a good one. So for example, we spend a whole lot of time talking about the mathematics of the sciences without really relating them to the sciences that a lot of people are going into, specifically engineering. Transformations are extremely important in physics and engineering. Okay, what does this transformation do? In engineering, it's important to look at transformations that take objects in one vector space and move them around. Take objects in one vector space and move them around, or stretch them, or flip them in some sense. I'll leave it at that. So let's take a look at this transformation. So what is this what two vector spaces is this transformation operating? It's operating within the same two vector spaces. It's taking an element of R2 and turning it into another element from R2. And we can view R2 as the XY plane. So specifically, what's it doing? Okay, let's take a look at a point in the XY plane. Here's R2, the XY plane. And here's a point. I want to stretch out the x-axis a little bit. Here's oops, gotta get it out of the erase mode. Here is the XY plane, and here's a point. I left it with erase again. Sorry, guys. Here is the point X, Y. Okay, so there's the point X, Y, or in terms of column vectors, X, Y. Oops, remember that using ordered pairs to designate points is only one kind of notation that's used to do that. We could use vector notation. Matrix notation to designate a point. So here's the point xy, expressed as a column vector. So the transformation takes xy and leaves the y component alone, or leaves the y coordinate alone if we're thinking in the xy plane, and doubles the x coordinate. So it takes the point xy and turns it into 2xy. So it took the point P and moved it to the point Q. Specifically, it takes a point P and doubles the x value. It scales the x value, the x component by 2, or multiplies the x coordinate by 2. So it moves points to the right or to the left, depending on whether x is positive, and doubles the x coordinate. Okay. There are transformations that take entire portions of the xy plane and scale them bigger or smaller, or, well, again, I want to leave it there because we have a lot to talk about. It's a very exciting topic of the idea of what what transformation. I keep using the term that we're heading for. What transformations do to either single elements in R2 or R3, or to entire portions of regions in those spaces. Okay. Well, let's see. Again, we really haven't started with the topic of linear transformations. I'm trying to get you used to the concept before we dig in. I realize this is going on about examples, but it's real important that we understand what a transformation is before we start talking about them. So let's let T take ax plus b. So in what vector space is ax plus b? See if you can remember. That's a good review of vector spaces. In what vector space is an object of the form ax plus b as a and b range through different scalars? It's P1, instead of all polynomials of degree 1 or less. How could it be less? Well, if a is 0, it's instead of all polynomials, constant polynomials, degree 0. So let's let t of ax plus b equal 2ax squared plus 3bx. Okay, so t takes something in P1 and turns it into a vector into something in the what's the vector space that T is taking an element from P1 into? P2, taking it into the set of all polynomials of degree 2, 1, or 0, a set of all polynomials of degree 2 or less. Specifically, here's I'll write the formula for the transformation again, and then we'll look at some specific transformations. T doesn't take real numbers into real numbers. It's taking entire polynomials and turning them into other polynomials. So T is taking x and turning it into what? What's T of x? Well, T of x I obtain by letting A equal what? 1, and B equal what? 0. Oops. So, let's see here. I want to make this even more clear. Okay, I still want to do the same thing. T takes T of x. T of x is the same thing of T of 1x plus 0. Okay, so I'm going to substitute A equals 1, 2 times 1x squared, plus B is 0, plus 3 times 0x. So that's 2x squared. So T of x is 2x, okay, squared. So T takes the polynomial y equals x and turns it into the polynomial y equals x squared. So what does T take x minus 1 and turn it into? It turns it into, well, first of all, x minus 1 is 1 times x plus negative 1. So A equals 1, 2 times 1 times x squared, and B equals negative 1, 3 times negative 1 times x. So it turns it into the polynomial, or the quadratic, 2x squared minus 3x. So what's the 0 vector in P1? What's the 0 vector in Pn? Remember, Pn is a set of all polynomials of degree n or less. So the polynomial of degree 0 would be y equals 0. So let's see what T takes 0, the 0 polynomial, turns it into. Remember, this 0 polynomial is not viewed as the scalar 0. This is the polynomial y equals 0. This is T. It's taking 0 times x plus 0 and turning it into 2 times a times x squared plus 3 times 0 times x, which is 0. And that's the 0 vector in P2. So again, we're getting something that appears to be universal. It is not universal, but it appears to be universal that these transformations between vector spaces take the 0 vector in one vector space and turn it into the 0 vector into another in the other. And it is not true. It is not always true. Okay. But under the best circumstances, it is true. It is under the circumstances of in the context of our course, it is going to be true. But we have to polish this up and consider only special kinds of transformations. Okay. Let's see. So let's start this chapter. Let's head toward the concept of a linear transformation. Well, we need to be real formal with our notation. So we're changing our point of view of functions. So if for example we're going to consider a function from a set x, and I'm not saying it's a set of real numbers, but very often for us it has been, from a set x to a set y. Okay, we write we write f takes x, something in x. It's not taking a specific element of the set x. This is a set capital X. It's taking x into another vector space, another set. We're not talking about vector spaces yet. Set y. Okay. We say f maps x to y, and sometimes we use the word into instead of just to y. Okay, so there's our function again. It takes something from one set and turns it into something from another set. The first set is called the domain. And don't get carried away and try to anticipate what we call y, because it's not the range. the set that the function turns something from x into is not called the range. It's called the codomain. Codomain. Okay, we'll clear that up in a bit. Sometimes it's called the image set. Okay, not the range. Some of the elements from the image set are the range. Okay, now if you're a little worried about this codomain business, it's no big deal. Let's go back to a very simple function. Let f take the real numbers into the set of the set of real numbers again by the function f of x equals x squared. Okay, so here is a graph of this situation. My attempt here is to differentiate. I don't mean derivative, but to show you the difference between the codomain and this thing we're going to call the range. So we obviously we know what the function looks like, the graph of the function. Oops, oh, that's really the sloppiest parabola I've made. It's not much better. Okay, so obviously from algebra 1 we know what the graph of this function looks like. Okay, so remember, the domain of a function is a set of all x values that are allowed in the function or used in the function. So the domain is a set of all real numbers. So this is the domain. Okay, the domain. What's the range? Well, the range is what comes out of the function, the set of all y values that get used by the function. So let's put the range in a different color. Let's see. Let's put the range in, I don't know, blue. Okay. Well, none of the negative y values are used in a range. So the range is up here. I'm going to clean that up a little bit. Let's say here. Here's the range. Trying to get, here we are. Here's the range. Trying to get a marker to work here. I think it was the fattest arrow I've drawn today. Here's the range. Range. So the range is a set of all non-negative real numbers. Okay, we're used to this from algebra. So the domain. In algebra, we call it the natural domain. It's a set of all real numbers. R, or a set of all real numbers. Negative infinity to positive infinity. Range, the set of all non-negative real numbers, 0 to infinity. Okay, so what's this codomain business? The codomain is the set of all y values, period. Set of all real numbers. Here, let me show you let's see if orange shows up. This is our codomain. The codomain is the set that the range is for us it's going to be a vector space, but it's the set that the range is part of. Okay, this is the codomain. Codomain. Oh, I don't like this fat pen now. I guess there's no pleasing me. I want the fattest possible pen for the arrows, but not for spelling. This is the codomain. That's not hyphenated. Codomain. Okay. So, and this was mostly the case for us in all of the math that we've taken except for Calc 3. The functions that we deal with take a real number and turn it into another real number. They take a real number from a specific set of the domain and turn it into a real number. The set that the elements are turned from the domain are turned into come from the set of all real numbers. That specific set of values in the codomain in the set of all real numbers where these y values actually end up, that's called the range. Okay, so the range is the part of the codomain. So the range is the part of the codomain. Codomain that gets used by the function. I like that's the way that works out. Y equals x squared ends up as a real number, but only the positive real number or non-negative real numbers are those numbers that get used up. Okay, so and that's the range. So more technically, it's the set of all f of x values such that, oops, that's a terrible vertical line, such that x is in the domain. Okay. Okay. And in algebra we called that the set of all y values. Set of all y values. Okay. I hope this is clear. I'm going to look at an example from Calc 3. If you haven't had Calc 3, because it's not a prerequisite for this course, don't worry about it. This is just to enhance your knowledge of the if possible, knowledge of the terms domain, codomain, and range. So let's let G take something from R2 and turn it into something in R. By the formula G of x of the column vector xy equals x squared minus y squared. Okay, so G is taking a column vector or a point in the xy plane if you want to imbue it as a column vector and turning it into a real number. These in Calc 3 are called surfaces. In Calc 3 we would write G of xy equals x squared minus y squared. So this is our old notation. We'll say old notation. Probably not any older than this notation, but for us it's old notation. And if you haven't had Calc 3, don't worry too much about this. We did look at, in this course, functions of more than one variable when we talked about exact differential equations. But if you're not comfortable with it, you can just ride this example and just, okay. So, what is the domain of this function of two variables? The domain is the set of all points from the xy plane, or the domain is R2. So what's the codomain? The codomain is what those points in R2 are turned into. The codomain is that vector space that those elements that from R2 are taken into. Okay, so if I enter, if that didn't make sense, I don't like my word verbiage on that either. For example, G takes the point 1, 2 and turns it into 1 squared minus 2 squared, or 1 minus 4 negative 3. So G takes a point in R2 and turns it into a scalar. So the codomain is the set of all scalars, all real numbers. Okay. The range is the specific part of the codomain that these elements are taken into. Okay, which may be the whole codomain or may be a restricted part of the codomain. So, can you see? And this is a really tough question, even for a Calc 3 student. Can you see what the range is? Is the range all real numbers or just positive real? It's obviously not just positive real numbers, because I showed you that the point 1, 2 gets turned into negative 3. Is it the set of all negative real numbers? Is it always negative? Is it always positive? What? In fact, it's R again. The range is R again. Now I'm going to ask you to think, if you've had Calc 3, why that might be true. How could you justify that? So if you haven't had Calc 3, don't worry about it. It's not, your grade isn't going to be dependent on whether you can show that the range of this function is all real numbers. And I want you to think about it. It'll enhance your thinking and get you about transformations and get you more used to thinking about transformations. If I were to graph g of xy equals x squared plus y squared, that's basically what I'm asking you. What does it look like? Your hint is that it's a quadric function. Quadric surface. Okay. So you have to remember what quadric surfaces are. They're like paraboloids and cones and hyperboloids of 1 sheet, hyperboloids of 2 sheet. I left out the one that this one actually is. Well, this one's the roughest one. It's called a hyperbolic paraboloid. So I'm not going to go through how to graph it. That's something you do in Calc 3, or we would do in Calc 3. But I'm going to graph it for you. And from the graph, you'll be able to see. And again, if you haven't had Calc 3, don't worry about it. But if you had had Calc 3, you can get an idea of why the range is actually all of the codomain. So now I'm going to be reorienting the axes from the usual orientation. So x, positive y, going backwards, and z. And here's the graph of this surface in, well, let's stay in green. Graph of the surface. You're not going to have to graph these on a test for me, or ever for me in this course. Okay. But the graph nevertheless reveals, that the range of this function, of this transformation, is in fact all real numbers. So it's a saddle. It's a saddle. But this saddle extends forever up, forever down. That's important. That says that the range is all real numbers. You take an x-coordinate, you take an x-coordinate and a y-coordinate, and you go up to the surface for the z-coordinate, x, y, z, where z equals g of xy. Every possible z value happens. Positive z values, negative z values, and 0. The function takes the origin, turns it into the origin. So, it turns it into 0, sorry. Okay. It's easy to do this without the graph. What's f of x? 0. It's x squared. X squared is always positive, or 0. what's f of 0y? It's negative y squared, and that's always negative. Okay. Okay, so this tells you that we get the set of all real numbers. Okay. So finally, 40 minutes into this this lecture, finally 40 minutes in. Oops. And we can talk about linear transformations. Okay. If you've noticed, I'm having some technical issues here with Camtasia, or with my. I'm trying to be very careful here. Okay. Hang on a second. Sorry, guys. Okay. Okay. For some reason, some very well-decorated room keeps popping up, too. That's my screensaver. All right. So linear transformations. Let's talk about what a linear transformation is. First of all, they are transformations. They're functions that between two vector spaces. So, definition. If V and W are vector spaces, so we start with two vector spaces. A function T, which takes elements of V and turns it into elements from W, is called a linear transformation. Our goal to study linear transformations. If for every two vectors u and v in the vector space V, and for every scalar C, so for every C in R, then the following two properties hold true. So if V and W are vector spaces, a function from T vector space V into W is called a linear transformations if for every two vectors in V and for every scalar, the following two properties hold. Properties hold. Two things have to happen. Okay. One, T of U plus V equals T of U plus T of V. Almost no function that you've studied works this way. Almost no functions work this way. Okay. So what we say is that T preserves addition. Addition in one vector space, in the vector space V, is U plus B. T in the other vector space is T of U plus T of V. So we have the preservation of addition. So 2. The function takes C times V and turns it into C times T of V. Also something that almost no function that you've studied ever does. Okay, for example, f of x equals sine of x. 30 years in, I've had a lot of students get really, really bad grades in calculus because they would like to have this function preserve multiplication. F of cx is sine of cx is not equal to c times sine of x. Almost none of the functions that you've ever studied works this way. Okay, so we say that the linear transformation T preserves scalar multiplication. multiplication. I'll explain to you again what I mean by preservation of addition and scalar multiplication. If the two vector spaces v and w are the same, if t takes v into v again, then t is called a linear operator. Okay, so let's get away from the concept of linear operator, just be more general about what we mean by linear transformations. Here's a vector space V. Let's say this is, that can be neater. I'll just use the rectangles. Here's the vector space V. Here's the vector space W. And the linear transformation is a transformation operating between these two spaces. So here is, if this dot is u and this dot over here is v, then we know that u plus v, because vector spaces are closed under addition, then u plus v is somewhere in there. So u plus v is in v. And the linear transfer, if the operator is a linear transformation, if the transformation is linear transformation, it's going to take u plus v and turn it into t of u plus t of v. So something was added together in v, and off in w, the transformation sent u plus v into another sum. So addition was preserved. Now the additions are most likely entirely different additions. So the plus in v and the plus in w are entirely different things. Remember, our vectors, one of the vector spaces, for example, or one of the transformations we looked at, turned something from R2 into the set of all 2x2 matrices. So addition in into those two vector spaces is very different. So while we have preservation of addition, it's not preservation of the same addition. And for the same reason, we call the second principle preservation of scalar multiplication. So if v is in there, then CV, if v is in v, the vector space v, then CV is in there, because we have closure under addition and scalar multiplication. But a linear transformation will turn that into c times t of v. So a scalar multiple of a vector in the vector space v gets turned into a scalar multiple of another vector in w. Those multiplication operations are entirely different in general. C times v is whatever the operation of multiplication is in the vector space v, and c times t of v is that different, most likely or potentially different multiplication in w. W may not even be resemble the vector space v at all. Okay. So let's work with some linear transformations. What I'd like to do is to look at an example that asks us to determine whether we have a particular transformation is a linear transformation. So, for example, determine whether the following function or transformation, if you will, is a linear transformation. Okay, and the function is t, which is going to take something in R3 and pop it into the vector space R2 by the formula t takes x, y, z and turns it into x, the column vector whose components are x plus y minus z and x plus 2y plus z. So it takes something in 3 space, if you've had Calc 3, we use the term 3 space for R3, turns it into something in 2 space. He's taking something in 3 space and turning it into something in the XY plane. Okay, so I want to see if this is a linear transformation. So I need 2 things to happen. I need 2 things to happen. I need one, t of u plus v equals t of u plus t of v. So let's see if that happens. So let's take 2 things from R3 and apply the linear transformation to that. So let's find t of 2 things from R3. Too much coffee. So there's one thing from R3. x1, y1, z1. So t of x1, y1, z1. That's our u, and here's v. x2, y2, z2. Okay, and I'd like to see what the transformation of the function takes this sum into. Well, let's perform the operation of the sum. x1, y1, z1 plus x2, y2, z2 as column vectors is the single column vector x1 plus x2, y1 plus y2, z1 plus z2, assuming the standard operation of addition in R3. Notice that I don't have the parentheses anymore, as they're not necessary. You can put them in or you can leave them out. Say I put the parentheses in, leave the parentheses out. It's your choice. I'm going to leave them out because it's a little more efficient to look at. Okay, so just off to the side, note it's perfectly legitimate to write t of u or simply tu. Okay, if you're a math major, expect your upper division math professors and further graduate professors, they're going to write tu for t of u. It's so much easier just to write tu than use parentheses. Okay, we weren't allowed to do that in calculus. If we want to write f of x, we can't write fx, but we're allowed to do that with linear transformations whenever it's not ambiguous. We couldn't do that earlier on. We couldn't do that here because we needed the parentheses to indicate that the transformation is taking the sum and not just one of the vectors into something. We needed the parentheses for the left-hand side. Okay, so onward. So let's see if we can get this first property to hold true. Well, we have now the operation that the transformation is defined as at our disposal. So let's see what t takes this x1 plus x2, y1 plus y2, and z1 z2 into. Well, t takes x, y, z into the column vector x plus y minus z. First component plus second component minus third component. First component, x1 plus x2, plus second component, y1 plus y2. It's tedious. Minus third component. A lot of the math for sciences, upper math, advanced engineering math, a lot of it is very tedious, okay? Even with some nice notation that you learn along the way for making things easier. So the second component is x plus 2y plus z. First component, x, plus the second component, twice the second component, 2y, 2 times y1 plus y2, plus the third component, plus z1 plus z2. Okay, and we want to see if we can make this t of the first vector plus t of the second vector. Well, I'm going to rip apart this column vector. I can write this as the column vector x1 plus y1 minus z1 x1 plus 2y1 plus z1 plus x2 plus y2 minus z2. This is after I've just gotten rid of the parentheses in the expression above, in the vector above, and rearranged terms and grouped into the sum of two separate vectors, just using matrix operations that we familiarized ourselves with a very long time ago in this course. Well, this is T of x1, y1, z1 plus T of x2, y2, z2. Check. That we have one holding. This is T of u plus v equals T of u plus T of v. If you're in any doubt, we start with T of u plus v, and this is T of u plus T of v, with or without parentheses, okay? So far it's looking like a linear transformation, but a linear transformation has two parts. We also need T of constant times a vector is constant times T of the vector, T of v. You could write it like that, or parentheses. It's either way. So let's see what the transformation does to C times something in the vector space, x, y, z. Oops. I'm not free to use brackets everywhere I want. T takes C times x, y, z. Parentheses are necessary here. They are necessary. They need to group C times x, y, z. And this is, well, first of all, what's C times x, y, z? It is the vector whose components are cx, cy, cz. No parentheses necessary here. You can put them in or leave them out. But what does the operation T do? It takes a column vector and it turns into the first component. I already forgot what it does. First component, I'm getting old, plus second minus third. First plus second minus third component. And the second entry is first plus 2 times the second plus the third. I think. First plus 2, yes. Now I want to see if I can get that constant C out. Of course I can. This is nothing more than C times x plus y minus z, the vector whose components are C times x plus y plus z, and C times x plus 2y plus z. And we're assuming that we have the usual operations of addition and scalar multiplication on R2. So I can factor, if you will, the constant out. And this is C times what the transformation does to the vector x, y, z. Done. Check. Done. Done. I've shown that T of CV, a constant multiple of a vector, is a constant multiple of T of the vector, T of v. Okay. Okay, so let's move on. If you haven't discovered, this is a very, very long section, so feel free to take a break at any point. And this would be a perfect time, or you can, let's see, what's a natural place? If you can hold on for, say, 10 minutes, that would be great. Or you can take a break now. Okay. Or you can just, yeah, you just keep going if you want. So now consider T taking something in R2 and turning it into something else in R2 by T takes xy, the column vector xy, and obviously it's got to turn it into another column vector to stay in R2. So x squared is the first component, x plus y plus 1. Okay. Now, if you noticed, I'm staying very, very close to the text with these examples and adding my commentary. This is on purpose. This is very difficult reading. So I'm trying to make things as much as possible correlate between lecture and text. That's going to end in section 5.3, and it's a good thing. I'm going to give you a much easier to digest version of 5.3. 5.3 is considered by some to be the most difficult section in the whole textbook. But I think I can make it not so. So anyways, back to this. So your author shows the first that the first property doesn't work. I'm going to show you the second property doesn't work. All you need is one of the two properties not to work, and it's not a linear transformation. So I'll do the second one. Okay, so we need 1 and 2. Again, I'm going to do 2 because it doesn't work. We need T of CV equals C times T of V. Okay, or if you want to put parentheses in, that's fine. So let's see what T takes a constant. Well, oops, I'm not free to use brackets that way. Let's see what T takes C times a vector and does to that vector. Well, the C times a vector is nothing more than the vector whose components are Cx, column vector, Cx and Cy. Okay, and what does the transformation do to that Cx, Cy? It turns it into Cx squared, and then Cx plus Cy plus 1. Okay. Well, let's see what we need to have the linear transformation turn C times xy into. So let's separately look at the left-hand side, the right-hand side, the other side. Okay, so here's the left-hand side. That's T of CV. Let's see what the right-hand side needs to look like. The right-hand side needs to be C of T V, V being the column vector xy. Well, that's C times x squared, x plus y plus 1. Okay, and we have the operation of scalar multiplication. It says I can bring that constant in. It looks like Cx squared, Cx plus Cy plus C. These two things that we end up with in left-hand side and right-hand side are not equal. These are not equal. These are absolutely not equal. So T is not a linear transformation. So T is not a linear transformation. Number 2 fails. Number 1 fails also, but number 2 fails. Transformation. Okay, i.e., that is, T of CV is not equal to C times T of V. Okay, let's get away from matrix transformations. So that we need to look at examples of other kinds of transformations. So consider a transformation that takes, we'll use a one we've looked at already. The function that takes P1 into P2 by T of AX plus B equals 2AX squared plus 3BX. We looked at this one. Is this a linear transformation? Is it a linear transformation? 1. What does the linear transformation do to U plus V? T of U plus V. So let's see what the linear transformation does with U. A1x plus B1 plus V. A2x plus B2. Parentheses necessary here. Okay, well, let's work inside the transformation first. We're inside the transformation, adding up two things from P1, which can very easily be written as A1 plus A2x plus B1 plus B2. I'm just adding those two polynomials up. So now let's see what the linear transformation does to this. It turns ax plus b into 2ax squared. Oops, no more t. 2ax squared. 2a, which is now a1 plus a2, x squared, plus 3b, which is now b1 plus b2, x. Now I would like that to equal t of the first polynomial plus t of the second polynomial, and I think we can do that. Let's distribute and combine like terms. Let's distribute and rearrange. So I'm going to have 2a1 x squared. I'm also going to get 2a2x squared, but I'm going to rearrange terms. I'm going to get 3b1x, lump those two together. I'm also going to get 2a2x squared plus 3b2x. And that is t of a1x plus b1 plus t of a2x plus b2. So one holds. We got one holding true. So check. You don't have to put a check if you don't want. You just move on to the next one. So 2. I want to know what t does to CV. C times something in there. ax plus b. You can call it a1x plus b1 or a2x, or just ax plus b, since we're only using one vector. Well, c times ax plus b is cax plus cb. That's the operation of scalar multiplication in P1. Okay, so what does t do to this particular vector? It turns it into 2 times cax plus 3 times the b, which is now cb, x squared, and cb, 3 times cbx. Okay, this is just a quadratic. It's just simply a quadratic. And what can I do with that c? I think if you can see what I'm doing here now, if it was natural for you to think, well, factor out that c, then you're on your way with linear transformations. They're not that rough. They're just new. And this is just c times t of ax plus b. Check. We got 2 happening. So t is a linear transformation. Those 2 properties hold true. Okay. At this point, you might want to take a little break, because we're gonna continue on with a specific, very, very important type of linear transformation. Then we're going to look at a theorem of general properties of linear transformations. So it doesn't get too wild, but it is going to be new stuff. So if you want a little break, you might want to stop. In fact, I'm going to stop and take a little break. And you will. I guess you won't know how long my break is. It's just going to seem like seconds. Yeah, I'll be right back. Okay, so let's take a look at a specific type of linear transformation. Okay, let's take a look at a specific type of information. Let's look back at linear transformation. Let's take a look back at our first linear transformation. I think it was our first one. So let's let t take R3 into R2 by t of xyz is x plus y. I think it was minus z, and then down below in the second component it's x plus 2y plus z. Okay, we determined in our first example that this was, with linear transformations, that this is a linear transformation. Now I'm going to factor this linear transformation in a specific way. I'm going to, with the linear transformation, the entries, I'm going to put the coefficients of x, y, and z in there. 1, 1, negative 1, 1, 2, and 1. Right? Let me make it a little clearer. And 1. I can even do a little better. Okay. So let's take the coefficients. 1, 1, negative 1, 1, 2, 1. And let's multiply by the column vector x, y, z. Let's take the coefficients and form a 2 by 1 matrix and multiply by, a 2 by 3 matrix and multiply by the column vector x, y, z. Okay. If you want, you can mentally do this multiplication and see that it's exactly our original linear transformation. Okay. This, if I can do this, then if I can do this, that is, write my linear transformation as some matrix times an element from the original matrix, the original vector space, in this case R3, then we have something called a matrix transformation. I can rewrite this as A, and I could write the column vector as capital X. So I'm looking at T of capital X equals A capital X. This is called a matrix transformation. T of X, capital X, equals AX is called a matrix transformation. Okay, and they're very, very important in STEM math, in science math. Okay, so let's take a look at a theorem from our textbook that has to do with matrix transformations. So we call that theorem 5.1. Theorem 5.1. Theorem 5.1 says, I'll say this in red, every matrix transformation is a, what do you think? Every matrix transformation is a linear transformation. I'd like to be able to go backwards too. I'd like to be able to go backwards and say every linear transformation is a matrix transformation. It turns out I can almost go backwards. That turns out to be the hardest point. The hardest part about linear transformations for us is the going backwards part. We'll talk much more about that. Let's not bite off too much. So I want to show that this is true. I want to prove this. Okay, so proof. I want to show that every matrix transformation is a linear transformation. So let's start. Let's let A be an M by N matrix. Okay. The theorem is saying that the linear transformation, the function, not the linear transformation, but the function, or just the transformation, T going from Rn, you have to get these spaces really carefully done here, Rn into Rm by T of X equals AX. Let's take off the word proof and write it in other words. In other words. Then we'll prove it. Let A be an n by n matrix. The function T going from Rn to Rm by T of X equals AX is a linear transformation. This is what we need to prove. Linear transformation. Don't worry if you're a little confused at this point. Okay, I'll try to clarify. Transformation. So just given a matrix, given an m by n matrix, if you pick something out of Rn, it will look like x1, x2, all the way up to xn. And if you multiply on the left by a, which is a11, a12, all the way up to a1n, am1, all the way up to amn. So there's A as an m by n matrix, and here's an element from Rn, an element from Rn, capital X, is an n by 1 matrix. Then the result, Ax, is going to be a what? Well, remember that the multiplication is allowed, and the result is an m by 1 matrix. Okay, that means we're in Rn. So the n by n matrix times something from Rn is somewhere in Rn. M. Okay. Okay. So let's prove this. Let's prove that it's a linear transformation. It's not difficult. It's not at all difficult. Proof. I'm going to show that t of x equals ax is a linear transformation. Two things have to hold true. Okay. One, let x and y be in where? Rn or Rm? Rn. So let's say what t does to the sum of those things. Okay. Well, t of x is capital A times capital X. So t of x plus y is A times capital X plus capital Y. Now, we started this course with a whole lot of properties of matrices. One of them is that we can distribute. A is a matrix, and x and y are matrices. We have a distributed property. But ax, that's t of x. Oops, there's no by. Yeah, no, it's no b, actually. I don't know why I have a b in there. I think I put myself on automatic here. Oops. Gosh. Maybe I need another break. Plus t of y. Okay, so 1 holds true. 2. Let c be a scalar. And let's see what the transformation does to cx or cy, it doesn't matter, cx, c capital X. Well, it is a times cx. Well, that constant can be factored out. This is just matrix multiplication. It's c times ax. This is c times t of x. Done. Checked off the two things. So every matrix transformation is a linear transformation. Every matrix transformation is a linear transformation. Now, two things, and I'm not even going to write these down, but they're very important things. Just hear them. I want you to hear them early. I mentioned them already. Every matrix transformation is a linear transformation. Okay, we just proved that. Every linear transformation, the converse is also true. The reverse of this is true. Every linear transformation from Rn to Rm is also a matrix transformation. We saw that for our specific example, that the matrix transformation that we looked at before, we could factor out the coefficient matrix and make it into a matrix transformation. But this turns out to be generally true. It's much harder to deal with, but every linear transformation, whether it's from Rn to Rm or from P1 to P3 or whatever, is in some sense given by a matrix transformation. This is very difficult. This is section 5.3, often considered the most difficult part of the course. So it turns out that basically every linear transformation somehow, in some way, not exactly, but in some way is given by some sort of matrix multiplication. Okay, so if you missed that, the last minute and a half, it's not critical for section 5.1. Let's just stick with our topics. Okay, so. Along those lines, we have an important theorem. I want to state the theorem and I want to prove it, but I'm going to prove the theorem a lot differently than your textbook does. I like my proof better. If you like his proof, that's fine. But it's not all about me. It's all about you guys learning this stuff. So let's start with a linear transformation. Let's let T go from V to W be a linear transformation. Be a linear transformation. What did we notice about what was something in common way back, almost a couple hours ago, when I just started talking about transformations? It seemed like the zero vector in one space was transformed into, by the transformation, we didn't have the word linear transformation yet, was transformed to the zero vector in the other space. This is always true for linear transformations. This is always true. So the first part of this theorem is that that T of the zero vector in V equals the zero vector in W. Your author doesn't use this notation, and you don't have to use this subscript notation either. He just says T of 0 equals 0. But it's misleading, because those zeros are zero vectors in what could be wildly different vector spaces. V and W could be very, very, very different vector spaces, and their zero vectors could be different. But if you have a linear transformation, the zero vector in one space gets transformed right into the zero vector in the other space. I'm going to prove it differently than your author does. Okay, so I'll prove it in red. So proof. Okay. My proof starts out with, let V be in the vector space capital V. So what justifies that? That's just that very first step. What justifies picking something out of V? Because vector spaces are not what? They are not empty. Okay? All vector spaces are, there's no such thing as an empty vector space. What element do they at least contain? Well, they at least contain the only element that existence is by the only property that states that we have to have a specific element, and that's the zero vector. Okay, so let's pick something out of V. Okay, so T of 0 in V is equal to, well, if V is in the vector space, then so are scalar multiples of V. In particular, 0 times V is in there. But 0 times V equals 0. That was a theorem that we proved. 0 times V equals 0, the zero vector in V. Okay, so T of 0 is T of 0 times V. But T is a linear transformation. So that scalar, that's 0 right there. That's the scalar 0. We factored out. Why? That's property 2 of a vector of a linear transformation. And what's any scalar? What is the scalar what is the scalar 0 times any vector T of V? That is the zero vector in V. Okay, if you didn't see what I just did there, I picked something out of the vector space V. I picked V out of the small v out of there. Okay. The 0 vector in V is also there. Okay. And it looks like 0 times V. The 0 vector, 0 sub V, is also in there. So is 0 times V. In fact, we showed that 0 times V equals the 0 vector in V. Okay, so the t of 0, the 0 vector in V, equals t of 0 times V. Okay, but we know that by property the second property, property number 2. Oops, and I caught the mistake. T of the 0 vector, the 0 times V is in there, but by the second property, this is equal to 0 times t of V. Clean up that little arrow here. The 0 vector in V gets taken to t of the 0 vector in V, which is 0 times V. But the second property says I can factor out the 0 scalar. And what's 0 times the 0 scalar times a vector? It is the 0 vector. The 0 vector where? Let's see if you caught my mistake. Okay. So I made my little blunders made this look much more difficult than it was. It's really a simple proof. Okay. So t of 0 equals 0. The t turns the 0 vector in one space into the 0 vector in the other space. So the second theorem, t of the opposite of V is equal to the opposite of t of V. How in the world is that true? I'm not saying t of negative 1 times V equals negative 1 times t of V, and I'm saying t of the opposite of V gets taken to, it equals the opposite of t of V. Okay, the proof is also very simple. Proof. Pick something out of the vector space. So let V be something in there. So t of negative V equals, now we have a theorem that says that the opposite of V is negative 1 times V. Way back. So that's how we introduce the scalar negative 1 into this. But the second property says, for linear transformation, says that scalar can be factored out. Okay. Now we're in this quantity, negative 1 times t of V, that's in W. And we also have a theorem that says negative 1 times a vector is the opposite of the vector. Okay, so there's a little QED on that. Here's a QED on our first one. So, number 3. So number 3, what do you suppose t of u minus v is? T of u minus v is t of u minus t of v. Okay. I'll do the proof real quick. It's very straightforward. Proof. The proofs here are just mostly to remind you of the operations that are allowed in vector spaces and the theorems from vector space. We're going to need all the mechanics of vector spaces that we learned before taking a trip into differential equations land. And it's been about 3 or 4 weeks since we looked at vector spaces. So the proofs are good for you in that sense. So proof. Pick 2 things out of V. How can I pick 2 things out of V? I'm only guaranteed that there's at least one thing in there, the zero vector. Well, if pick two things out, if there's only one thing in there, then they're both equal to that, that zero vector. Okay, so pick two things out of the vector space. Okay, and let's prove it. T of u minus v. Well, the definition of u minus v is u plus the opposite of v. That's the definition of u minus v. Okay, but the first property of linear transformation says that this is t of u plus t of the opposite of v. But we just finished showing that t of the opposite of v is the opposite of t of v. Okay, and this is, now we're adding up two vectors in the vector space W. T of u plus the opposite of t of u. The definition of that is t of u minus t of v, QED. Okay. Number 4 I won't prove. Number 4, and you're not responsible for the proof. So, but it's a pretty obvious thing. Okay, it's a real important identity, actually. All of these properties result in us being able to do this. T of C1 V1 plus C2 V2 plus plus Cn Vn. What is that quantity? Not with T, but C1 V1. What is it called? C1 V1 all the way plus C2 V2 all the way up to Cn Vn. That's called a what? It's called a linear combination. Okay, so again, I'm just trying to review topics that we've talked about. So the number 4 is the ultimate important part of this theorem. It says that the linear transformation turns linear combinations into linear combinations, and the linear combinations off in the space W look like C of T of V1 plus C2 T of V2 plus plus Cn times T of Vn. So what does T preserve, if we're going to use the concept of preservation? Remember, T preserves addition and scalar multiplication. T preserves linear combinations. Linear combinations in one space, V, get turned into linear combinations in another space, W. Okay. Okay. All right. So we're going to look at some pretty hefty examples coming up here. So again, you may want to take a break, or you can push forward. It's actually one example with 2 parts, but they're pretty notation intense here. So here it is. Example. We're given we're working with a linear transformation from R3 to R2. Okay, and we're given a particular basis for R3. So given that, that these 3 vectors, 1, 1, 0, from R3, 0, 1, 1, and 1, 0, 1, form a basis for R3. Oops, RM is R3. Good grief. So what does that mean? Just this first statement. Given that these 3 vectors from R3 form a basis for R3. So what is a basis? A basis, this vector, this set of 3 vectors form a basis if every element in R3 can be written as a linear combination of these 3 vectors. That's one part. What's the second part of a basis? That the 3 vectors are what? They are linearly independent. Okay, so remember, a basis for a vector space is a set of vectors that both span the vector space. In this case, every vector in R3 is a linear combination of these 3 vectors, and those vectors have to be linearly independent. Okay, And I referred to a basis as sort of a minimal spanning set. So any basis for R3 must have how many vectors in it? 3. If you have more vectors in it than 3, they're automatically linearly dependent and don't form a vector space. Don't form a basis. You can't have 2 because 2 vectors are not enough to span. Okay, so every basis for R3 has 3 elements. It's a minimal spanning set. Okay. Also, given that, and that our linear transformation T takes the first basis vector into the vector 2, 3. So I guess I should preface this with, what is this T? Give me a second here. Let's wait for my computer to give me some space. There we are. Let T take R3 to R2 be a linear transformation and T takes the basis vector 1, 1, 0 to the vector 2, 3. T takes the second basis vector 0, 1, 1 to the vector, let's see, where do I want it to go? 0, 3. And T takes the third vector 1, 0, 1 and turns it into 0, 2. Okay, so I'm not giving a formula. I'm not giving a formula for the linear transformation T. I'm just saying let T be a linear transformation from R3 to R2, and suppose it takes the 3 basis vectors that I've identified and turns them into the 3 vectors in R2. Okay, from this, I want to find what T does to some other vector. I want to see what T does to the vector 1, 3, 0. I don't have a formula for T. All I know is its action on the basis vectors that I'm given. All I know is what T turns the basis vectors into. Okay, and just knowing that, I want to find T of something else. It looks like an unusable example, but this is really saying something important that's coming up soon. It turns out that if you know what T does to basis vectors, you can figure out what it does to any vector. That's what's going on here. Okay. So yeah, I want to really make sure that you're okay with this. So here's R3. Oops. And here's R2. 2 nice vector spaces. And the linear transformation takes the vector 1, 1, 0 and turns it into 2, 3. It takes the vector 0, 1, 1 and it turns it into the vector 0, 3. And it takes the basis vector 1, 0, 1 and turns it into 0, 2. That's all I know. This linear transformation does. Okay, so that's what the vector T does to these 3 vectors. So I want to know what it does to the vector 1, 3, 0. Okay. The first thing we want to do is we want to take the vector from R3, that 1, 3, 0 that we're interested in, and write it as a linear combination of the basis vectors. Okay. So first, write 1, 3, 0 as a linear combination of the three vectors of the three basis vectors of the basis vectors from R3. The ones that are given, not the standard basis vectors, but the ones that are given. Okay, and that's a little labor intensive. Okay, so I'm going to take 1, 3. I skip a lot of the details for that the computer or the calculator does, and you could do that too. Here's what I'm talking about. Take 1, 3, 0 and make it a linear combination of the three basis vectors 0, 1, 1, 1, 0, 1, and oops, sorry, the order of the vectors is messed up here. The first basis vector was 1, 1, 0, 0, 1, 1, and 1, 0, 1. Okay. How do I know I can do that? I'm asking a silly question. And I know it's silly. I'm not trying to insult your intelligence. So I'm just trying to review vector spaces. First, write 1, 3, 0 is a linear combination of the vectors of the basis vectors from R3. How do I know I can do that? Because basis vectors are precisely for that. That every element from R3 in this case can be written as a linear combination. So all I need to do is find C1, C2, C3. Okay, well that translates into a system of equations. This stuff is the same old stuff from before. So C1 plus C3 needs to equal 1. C1 plus C2 has to equal 3. And C2 plus C3 plus C3 has to equal 0. Okay, so using Gaussian elimination or Gauss-Jordan elimination method, either of those, I'll use the Gauss-Jordan method to get an RREF, reduced row echelon form, 1, 0, 1, and of course, feel free to use your calculator. Don't do this stuff by hand if you can avoid it. We can't always avoid it. We're going to see that soon. So if you find the RREF, you end up with 1, 0, 0, 0, 1, 0, 0, 0, 1, and 2, 1, negative 1. Okay. So that tells us what the constants are. So C1 equals 2, C2 equals 1, C3 equals negative 1. All right. So now let's do this. So let's find T of the vector. Remember the idea was I know what the transformation does to the three vector the three basis vectors. I know the action of the linear transformation on the basis vectors. The basis vectors 1, 1, 0, 0, 1, 1, and 1, 0, 1 get turned into those three vectors from R2. So now I want to find T of 1, 3, 0. Well, it's going to be T of the linear combination of the basis vectors that 1, 3, 0 can be written as. That didn't turn out real. I don't like the verbiage on that. So 1, 3, 0 is C1 2 times 1, 1, 0 plus C2 1 times 0, 1, 1 plus negative 1 or minus 1 times 1, 0, 1. But I have that theorem before that said that linear combinations are preserved. This is T of, if you will, C1 V1 plus C2 V2 plus C3 V3. That last part of that theorem says that I can write this as C1 times T of V1 plus C2 times T of V2 plus C3, so minus 1, times T of V3. And I know what the linear transformation does to the basis vectors. I know the action of the basis vectors by the transformation. They get transformed into 2, 3, 0, 3, and 0, 2. 2, 3, 0, 3, and 0, 2. Okay, if you perform this matrix addition, you get 4, 7. This is important. This example is important. If we know the action of a linear transformation on a basis, then we can find the action on T of any element from V. I want to state that again. Okay, if we know, this is hugely important for us. If we know the action, that is what the linear transformation does, if we know the action of a linear transformation on a basis for V, we can find T of V for any V in the original vector space, in the domain space V. Okay, this is extremely important. Extremely important in linear algebra. Okay. The second part of this example is tough, but it's tough not in the sense of conceptually tough. It's just algebraically tough because we can't use a calculator to help us out. I figured out what the action of the linear transformation was on this new vector 1, 3, 0, just knowing the action of the transformation on the basis vectors. Now, I want to find something more general. I want to find what the transformation does to any point x, y, z in R3, or any column vector x, y, z. This is much more tedious, but the example is exactly, the idea is exactly the same thing. So, exactly. First write the arbitrary vector from R3, from V, the first vector space, as a linear combination of the three basis vectors. In this case, the basis vectors are 1, 1, 0. My writing. I don't know if you noticed, but my writing is extremely squiggly. And there's two things at play there. One, I drink a lot of coffee. Lots and lots and lots of coffee. I'm up until 4 in the morning every night. And I do most of my recording between 11 p.m. and like 4 or 5 in the morning. And two, if you've ever written on a surface, it's like trying to write with a ballpoint pen on a sheet of ice. It slides. So, and my writing has never been good, even in class, if you've had me before. So that makes for some pretty bizarre looking writing sometimes. And believe me, I'm trying extremely hard to be neat, but there's nothing I can do. I'm not trying to be sloppy here. I guess I could minimize that by not drinking coffee, but that's not going to happen. Okay, so first, write x, y, z in terms of the basis vectors. How can I do that? Because that's what basis vectors do. Anything from the vector space can be written as a linear combination of them. We need the hard part here. We need to find C1, C2, C3. So this is going to transform into the almost the same system that we had in the previous one, except the constants are not going to be 1, 3, 0. They're going to be x, y, z. Okay. And as I'm doing this, I realized an easy way to get the constant C1, C2, C3. I may take a break and verify it first. Okay, but we get the system. Too much information right now. C1 plus C3 equals X. C1 plus C2 equals Y. C2 plus C3 equals Z. Okay, I'm going to take a break for just a couple of minutes here. Try something. Okay, I'm back. I have good news for this. Earlier I said I'm being real close to the textbook with this and explaining some stuff in more detail and giving you my take on things. This is an example in the textbook on page 238. And I intended to do what your author did also, but something occurred to me just now. Let me explain. What we would have to do if we were going to continue the way we did in part A is we would have to by hand row reduce this augmented matrix for the system. I'm writing out the system and trying to talk at the same time. It would be almost the same augmented matrices that we had before, except we have a column of variables x, y, z. And this is not easy. It's not difficult either. It's just you have to keep track of a lot of you have to keep track of signs and do this by hand and keep track of sums and differences of multiples of x, y, and z, etc. You've done this before, and it's not that difficult. It's just time consuming. But it occurred to me that we could also use matrix inverses to do this. Okay, you could find the solution to this system by solving for C1, C2, and C3 instead of in fact you don't even have to use the Gauss-Jordan method. You could just use the method of substitution or whatever. In fact, I think I should show you what I had earlier. You could take the first two equations. I'll show you here. You could take the first two equations and subtract to get minus C2 plus C3 equals negative Y plus Z. I'm literally, plus X. I'm literally solving the system using intermediate algebra. Okay. And you could take the second equation, the last equation, C2 plus C3 equals Z, and then add those two to get 2C3 equals x minus y plus z to get C3 equals x minus y plus z over 2. Then you could solve for C1 and C2 similarly. Then similarly solve for C1 and C2. Okay, I'm not going to do it because I've got a better way to get C1 equals 1/2 x plus 1/2 y. Let's see, minus 1/2 c. And C2 as minus 1/2 x plus 1/2 y plus 1/2 c. So we've got C1, C2, and C3, and that would pretty much that would get us moving. But I want to use inverses instead, matrix inverses, rather than row reducing this, or not row reducing, but solving by hand. I'm trying to encourage you guys to use your calculators as much as possible. Ultimately, you guys are science majors, and you're going to be using computers and stuff to do this, to do your work. But we could set up we could take a look at the not the augmented matrix, but just the coefficient matrix 1, 1, 0, 0, 1, 1, 1, 0, 1. And off camera, I found the inverse. The inverse is, I still got it in my calculator, has a lot of 1/2s. 1/2s and negative 1/2s. 1/2, 1/2, negative 1/2. I don't know why your author didn't do this. I think I'm really surprised because I know his qualifications are much higher than mine with linear algebra. It was not my main field of study, and I think it is one of your author's main fields of study and all that. Anyways, so I'm surprised he didn't do this. So I'm going to write better way, but I'll write better in quotes because you may rather just solve the system by hand, and you're welcome to. There's nothing wrong with it. But remember, when you're solving a system, AX equals B, where A is a square matrix, M by M matrix, an invertible square matrix. So that's kind of a big deal. Then X equals A inverse B. Okay, our X is three constants, C1, C2, and C3. So C1, C2, and C3 should be A inverse times our B. Our column, our constant matrix is not in fact constant though. Remember, it's X, Y, Z. So this should be. I refuse to rewrite that, mate. I'm gonna copy and paste it off camera. Give me a second. Oops. There's A inverse. I just copy and pasted it off camera. Times B. X, Y, Z. So surprised your author didn't do this. Look at this. We get C1 equals 1/2 X plus 1/2 Y minus 1/2 Z minus 1/2 X plus 1/2 Y plus. I'm trying to be very, very careful here because I did not have this as a written part of my lecture. Plus 1/2 Z. So 1/2 X minus 1/2 Y. But I think it's far superior to doing this by hand. Whole idea with this matrices and stuff is to be able to use our technology to get things done. And a quick look will I'm looking to make sure that I did this right. They look exactly X minus Y plus Z over 2 for C3 X minus Y. Yeah. Okay. Cool. Very cool. Okay. So what did we accomplish? Let's not get too lost in all this matrix arithmetic. We were trying to find the action of the linear transformation on an arbitrary point in R3, X, Y, Z, if we just know the action on a basis. Okay, the very important thing is if we know the action of a linear transformation on a set of basis vectors, then we can find the linear transformation for any vector. That's real important. So I wrote X, Y, Z in terms of the basis vectors. That means I need to write X, Y, Z as a linear combination with C1, C2, and C3. I found C1, C2, C3. So, and this is a little more writing to do, but there's not a lot of work to do, just writing. So T of X, Y, Z equals C1, let's do it this way, C1 times T of V1 plus C2 times T of V2 plus C3 times T of V3, where the v1, v2, v3 were the basis vectors. So it's C1, a little labor intensive. Let's just write a factor out the 1/2. 1/2 times x plus y minus z. So T of v1 was, what did the transformation do to v1? It turned it into 2, 3. Okay, so T of v1 was 2, 3, T of v2 was 0, 3, and 0, 2 was T of v3. Okay, the v1, v2, and v3 were the original basis vectors. So T of v1 was 0, 2, God, I just looked at them and I forgot already. 0, 2, wait. 2, 3, 0, 3, 0, 2. Sorry about that. Watch your eyes. Sorry. 2, 3. 2, 3 plus C2, which is, factor out the 1/2 times negative x plus y plus z times 0, 2. God, I'm doing it again. It's 0, 3, and 0, 2 in that order. Sorry. Oops. This must be driving your eyes crazy. So plus C3 times x minus y plus z 0, 2. If you perform this matrix arithmetic, you end up with x plus y minus z, x plus 2y plus z. So the important thing here is if we know what the transformation does to each and every basis vectors in the domain, we can figure out what the transformation does to any vector, okay, in the original vector space. This is huge in linear transformation, in linear algebra. Okay. Okay, so what I did off camera is I summarized all this for you. There's a lot of stuff going on here. So below this line is a nice little summary. So in one sentence, the summary, just the one sentence, it says, once the action by a linear transformation on basis vectors is known, the action on any vector v in the vector space can be found. How? If v1 to vn is a basis for v, find t of v1 to t of vn. Find the action of the linear transformation on each of the basis vectors. Then go back to v and write an arbitrary vector v as a linear combination. That could be hard because you have to find constants, c1 to cn. Find the vector v, take your vector v and write it as a linear combination of the basis vectors. Then take t of both sides, take t of v. Then t of v is, by that last part of a theorem a couple of eons ago, t of v then is c1 t of v1 plus c2 times t of v2, etc. I had to park my motorcycle. I'm just kidding. A graph or sort of picture of what's going on is here is you have the basis vectors v1 to vn. Take t of them. Take the linear transformation of them. They get transformed into t of v1 and t of vn. Then take an arbitrary vector v and write it as a linear combination and take t of that. And the properties of the linear transformation allow me to write the result as c1 times t of v1 plus etc. up to cn t of vn, because linear transformations preserve linear combinations. Okay. Now, before we go on, if you haven't noticed, this section is one of the longer sections in the actual course. And we're not done. We have some work to do in this section. I welcome you to do, like as I've said, I welcome you to take this video in chunks. Take a break. You can your breaks don't have to be just a few minutes. You can take long breaks. So we have some more work to do. So far, I think we're at, oh gosh, where are we? We're at 2 hours. I anticipate another half hour, 45 minutes. So if you want to take a break, that would be perfectly fine. And then we'll continue once we keep seeing my screensaver of that beautiful room. Okay, so I'm going to take a break. I'll be back in a couple seconds. Okay, so now we're beginning the final stretch of this very, very long section. Okay, the next thing I'd like to talk about is a special set that's a couple of special sets that are related to or associated with a linear transformation. First is called the kernel, not like colonel in the army, but it's spelled differently. Kernel, the kernel of a vector space. Of a linear transformation. The kernel of a linear transformation is abbreviated KERT, and it's the set of all vectors V in the domain space, the space of the domain, such that T of V equals the zero vector in W. Okay, so if T is a linear transformation from V to W, then the kernel of T is everything that gets sent to the zero vector in W. So if this is our domain space, let's say V, and this is our domain, our space, the codomain W, and let's say U, the vector U in V gets turned into or transformed into the zero vector in W. V gets transformed into that same vector, and W gets transformed into that same vector. Since suppose that all three of these vectors get transformed into the zero vector in W, then those three elements are going to be in the kernel. So U, V, and W are in the kernel of T. So the kernel of T is everything in the domain space that gets sent to zero, gets turned into zero. We've encountered the kernel of a linear transformation before, although we didn't think about it this way. So let's imagine that we're looking at a specific kind of linear transformation. So let T from Rn to Rm be the matrix transformation. Matrix transformation formation T of X, T of capital X equals AX. Okay, so very specific kind of linear transformation. I'm trying to remind you where we've seen this. Then the kernel of T is, well, it's the set of all X, capital X, in Rn that gets sent such that T of X equals the zero vector in W. So the zero vector in Rm. Okay. Well, T of X equals AX. So it's the set of all X. When you recognize this, think to yourself, where have we seen this? It's the set of all X in Rn. Well, T of X equals AX such that AX equals 0. What is another name for this space. It is called the null space of A. Okay. So the kernel of a matrix transformation is nothing more than the null space of the matrix that defines the matrix transformation. So I'm going to bring up an old example with fresh eyes. We're going to look at it through a new set of glasses here, so to speak. So example, find a basis for the kernel of T. Okay, that's assuming a big thing just by saying this, that the kernel of T is a subspace of Rm. It is, because the null space, remember, is a subspace of Rn. So find the basis for the kernel of T if our old friend, the same linear transformation we've been looking at, if T of x, y, z equals, but I'm going to write it in sort of factored form, in matrix transformation form. So 1, 1, negative 1. 1, 2, 1, x, y, z. Okay, we've seen this. This is nothing new to us. This is just a new formulation, a brand new formulation of the same old problem we've done before. The kernel of a matrix transformation is nothing more than a null space, the null space of the matrix that defines the matrix transformation. So I need the null space of A. Okay, it's the set of all elements of Rn, R3 in this case, that get sent to 0. Okay, so we've done this before. So how do we do that? We solve the system, the homogeneous system, Ax equals 0. Okay, we solve the homogeneous system, Ax equals 0. So Ax equals 0, that implies that the augmented matrix is given here. I wrote it out. Use your calculator to find the RREF. This is 1. We get 1, 0, negative 3. I'm sparing you the row reduction because we don't have to do it by hand. We do this with our calculator. Okay. This says that x minus 3z equals 0. And y plus 2z equals 0. Okay, this tells us that, remember, we're looking for a basis for the null space. So this says that x equals 3z, y equals negative 2z. Okay, so the kernel of T is the set of all 3z, negative 2z, z, where z is the free variable, z is in R. Okay, that is, it's the set of all. What can I do with that? With the z, I can factor it out. Z times 3, negative 2, 1, such that z is a real number. That is, every element of the kernel is a linear combination of this one vector. Okay? So that shows spanning. So that vector, that one vector, forms a basis for the kernel of T, which is the null space of the matrix that defines the matrix transformation. What about linear independence? One vector is linearly independent. Okay, one vector. Uh, it, I'm thinking that's obvious, but I don't want to. I don't want to make too many assumptions. How do you show that a vector, a set of vectors, linearly independent? You form C1 V1 plus C2 V2 all the way up to Cn Vn, set it equal to 0. You need all the constants to equal 0. Well, C1 V1 equals 0. The only possible is since the vector V1 is not 0, the only possible value for C1 is 0. That means all the constants, namely C1, are 0. Okay, so that makes linear independence. So we found a spanning set, same stuff you did in the last exam. We found a spanning set. This one has only one vector in it, so one vector is automatically linearly independent. Okay, unless it's the 0 vector. Remember, no basis contains the 0 vector. So there. Let's take a look at a different example. Okay, so let T be the linear transformation from the set of all differentiable functions on the interval AB to the set of all functions on AB. Don't panic. This is not a difficult example. Given by T of y. T takes a function in the set of all differentiable functions, and then actually I want it to be in D2. Yeah, I need it in D2 because I'm going to be taking two derivatives. Set of all twice differentiable functions of y double prime minus y. Okay, so you enter a function, then you take two derivatives of it and subtract the original function. I want to find the kernel of T. Okay, you've done this. In fact, if you're up on homework and stuff, you've done this almost exactly. Okay, the biggest thing is understanding what is this kernel. Actually, we're not finding the kernel of T. We're finding a basis for the kernel of T. Sorry about that. My bad here. So find a basis for the kernel of T. Find a basis for. We've done it. So what is the kernel of a linear transformation? It's the set of all vectors that get sent to 0. It's the set of all vectors. It's the set of all functions y in D2 AB such that the linear transformation takes that to the 0 vector in the set of all functions, f. Okay. Well, let's be much more specific. What does T of y equals 0 mean? T of y equals 0 means y double prime minus y equals 0. So in this case, finding that a basis for the kernel doesn't result in or reduce to solving a system of equations. It reduces to solving a second order differential equation. We did this in section 4.2. It's a homogeneous one. So find the auxiliary polynomial or characteristic polynomial, whatever word you want to use, whichever the words you want to use for that. So you get lambda squared minus 1 equals 0. Lambda squared equals 1. Lambda equals plus or minus 1. So that means y, that value from D2 that we're looking for, y must be C1 e to the x plus C2 e to the minus x. Now, that's a solution to a differential equation. Think of this, though, as a vector. Okay, so what's all coming together here. Differential equations and vector spaces are not independent of one another. This y is a vector. It's a linear combination of e to the x and e to the minus x. Okay, so the kernel of T is spanned by e to the x and e to the minus x. That's not enough for a basis. Basis needs two things. Needs spanning and what else? Needs spanning and linear independence. Now we could get around that using some fancy theory that I think I brought up in chapter 4, that the dimension of the solution space to a second order differential equation is 2. Okay, so we could use the fact that since the dimension is 2, then any spanning set is also linearly independent. But we don't even have to do that. Okay, so kernel T is spanned by these two vectors. Are they linearly independent? E to the x and e to the minus x are linearly independent. Why? They are not proportional. Proportional. There's no constant you could find. There's no constant you could find to make e to the x. E to the x is not equal to a constant multiple of e to the minus x. Okay. Look at their graphs. They are not. One is not made equal to the other by a constant multiple. Constant multiples stretch away from the x-axis and stuff, and there's just no way you're going to do that. Okay. So, a basis for the kernel of T consists of e to the x and e to the minus x. Okay. Don't get lost in the specific examples here. The kernel of a linear transformation is nothing more than everything that gets sent to 0. So in this case, something sent to 0 means the function, when you take a second derivative and subtract y, you get 0, and that's a differential equation. So a basis for this kernel is, because of our work with differential equations, is just e to the x and e to the negative x. Okay. Okay. So we brought up an old set, the null space. The null space of A is nothing more than the kernel of a linear transformation if the linear transformation is a matrix transformation. What other space did we talk about when we were talking about null space? What other space were we finding bases for? We were finding bases for column spaces. Okay, so let's see how column spaces come into play when we're talking about matrix transformations. Okay, so here, example. How do I want to phrase this? Give me a second. Let's tear apart our old matrix transformation we've been looking at through the hours here. Let's consider our matrix transformation. T of x, y, z equals x plus y minus z. You're probably getting sick of looking at this same linear transformation. We're in the final stretch of the final stretch, though, here, so bear with me here. Okay. I want to examine the idea of finding a basis for the range of a linear transformation. We just finished finding or looking at a method for finding a basis for the kernel of a transformation. That is a basis for everything in V that gets sent to the 0 vector in W. Now I want to look over in W. I want to find a basis for the range of a linear transformation. So here's our linear transformation. T of x, y, z gets turned into this 2x1 matrix. So that 2x1 matrix is an element of the range. This is equal to an element of the range. Element, that's what they look like, of the range. of t, if you will. Okay, capital T here. Okay, now let's tear this vector apart. I factored it once one way. I want to factor it another way. I could write this as xx plus y, 2y, plus negative z, z. And from each of those vectors, I could factor out the x, the y, and the z. Now look back at the matrix of the transformation. Now recall the matrix of this transformation is just the 2x1 matrix whose rows are 1, 1, negative 1, and 1, 2, 1. Now look back at how I wrote the element from the range. The element from the range of this linear transformation is nothing more than a linear combination of the columns of A. Okay, so if you have, this is a big deal here, if you have a matrix transformation, it is a linear transformation that can be written as a matrix transformation, then the elements in the range, the elements in the set W, are nothing more than elements of the column space of your matrix. This is just a linear combination of the columns of A. So this is an element of the column space of our matrix A. You thought we were done with null space and column space. No, we were studying them for a reason, and this is the reason. Here is the bottom line result here. The range of T is nothing more than the column space of the matrix A. As long as your matrix is a matrix transformation. Remember, not every matrix is a matrix transformation, but as long as your matrix is a matrix transformation, you want the range, you want a basis for the range, you just simply find a basis for the column space, which we are experts at from our last exam. So we had just finished looking at the kernel. The kernel of a matrix transformation is nothing more than the null space of A. Okay, so these are two sort of summary results that we're looking at here. Both of those spaces, column space and null space, we've looked at before. We were able to find bases for those things by those multi-step procedure that I gave you for each of them. Okay, which most of you did pretty well on the test. So it's back. So exactly how would we use these ideas? Use this, in particular, this last idea that the range of the linear transformation is the column space of the matrix. Okay, so here, this is how it would play out on a typical homework or test question. Find a basis for the range of your linear transformation if t, the same old one, t of x, y, we're starting from scratch though, as if this were a problem. T of x, y, z equals x plus y minus z, x plus 2y plus z. Okay, well, I know that the range, since this is a matrix transformation, the range of this the linear transformation is nothing more than the column space of the matrix that defines this linear transformation. So the first thing to do is to find the matrix. In this case, it's very easy since we've seen it over and over again. So the matrix of this linear transformation, same matrix we've been looking at, that's our A. So how do we find the column space of A? This is a review problem. Okay, so first thing we did was we found A transpose. So this is old news. We found A transpose. 1, 1, negative 1, 1, 2, 1. By our work much earlier. No, it wasn't that much earlier. I'll just say earlier. By our work earlier in the course. 8, we find A transpose. We find the RREF of that. The RREF turns out to be 1, 0, 0, 1, 0, 0. By the way, the author of your textbook, he didn't find the RREF. He found just an REF. That's okay. If you want to read through his version of this example, it's just fine, but it's going to look different. And he doesn't explain why he doesn't go all the way to the RREF, because it's not necessary. All we need is a set of linearly independent vectors that span the vector space. Okay, for a basis. So he just found the REF. REF. I found the RREF. Okay, bases are not unique. Okay, so I found a different basis than he did. It's just as easy to find the REF as it is to find the RREF using a calculator. Okay, so first I row reduce the transpose. Okay, so what did we do? Basis vectors for the row space of B are 1, 0, and 0, 1. Okay, and just so we don't skip anything, they're linearly independent since they are not proportional. Almost forgot to state that. Okay, so because of that, we have basis vectors for row space of B. Okay, since the row space of A transpose equals the row space of B, because the row space of a matrix is equal to the row space of any row equivalent matrix. This was a theorem long ago. These vectors form a basis for the row space of A transpose. Okay, so basis vectors for the column space of A are 1, 0, and I realize I put commas in those vectors, and there shouldn't be commas, should not be commas, sorry about that, are 1, 0 transpose, which is 1, 0 is a column vector, and 0, 1 transpose, which is column vector 0, 1. Okay, but the range of T is equal to the column space of the matrix A that defines T. So basis vectors for the range of T are 1, 0, and 0, 1. So all the stuff we've learned before, it was just the beginning. It was just the beginning. Okay. Now, bad news and good news. What do you want first? Well, I'll give you the bad news. The bad news is we have one theorem to finish up. There's more stuff in the section than this last theorem, but we can stop at this last theorem. The remaining items after the theorem 5.3 are not too important for our future, not at all for future in the course. We're learning all this stuff about transformations in part so that you can do some really important things with this in your future from this course, but specifically in this course in chapter 6, when we start solving systems of differential equations, we're going to need this theory. Okay, so you're probably starting to really see, I think you probably saw this after calculus 1, that the math of the sciences is hard. It's hard. There's a lot to it. But this math that you're learning, this is the language of the sciences. Okay, so you're doing all this hard work for an important reason. The bad news, we have one more theorem. The good news is you don't have to prove it for me. If you want to read through the proof, it's fine. But the proofs are not particularly adding any kind of learning to this. If you're a math major, the proofs are important. But if you're a math major, you're likely to see this material again, where you will have to prove this stuff. So, for us applied math types, here's the last theorem with no proof. That's the good news. If t from v to w is and I'm going to abbreviate LT, linear transformation, then two things. One, the kernel of t, everything from v that gets sent to 0, the 0 vector in w, that part of v, the kernel of t, is a vector space, is a subspace of what? Well, where do the elements from the kernel come from? They come from the domain space, so a subspace of v. And 2, the range of t is a subspace also of what? The range, where is the range? The range is in W. So the range of t is a subspace of W. Okay, no proof, and you're not required to. Just realize that these two big items that took us back to some stuff we did earlier in the course, these two big items, the kernel of t, which relates to the null space of a matrix, and the range of t, which relates to the column space of a matrix, as long as your matrix is a matrix transformation. Those things are subspaces. Those things are actual vector spaces themselves. Okay. I want to thank you all for taking the time to look at this very, very long video. I hope you did it in sections and didn't try to look at it all at once. In any case, please get started on homework on this section as soon as you can while this stuff is fairly fresh in your mind, okay? And I'm looking forward to talking with you all again soon. Section 5.2 will be much lighter than this. Section 5.3, our target for all of this stuff, our target section for all these materials is another rough section, but we get a little break in 5.2, so I'll see you again soon.